Hi, I'm Natalie, and the question I'll be discussing is about interior angle sums of convex and concave polygons. So the question is, while studying convex polygons, the class determined that the sum of the interior angles of a convex polygon with n sides is n minus 2 times 180 degrees. A student asks, does the theorem concerning the sum of interior angles of a polygon hold not only when it is convex, but also when it is concave? So there's a couple standards I found that relate to this question. The first one is grade 7 geometry number 6. So it's solve real world and mathematical problems involving area, volume, and surface area of 2 and 3-dimensional objects composed of triangles, quadrilaterals, polygons, cubes, and right prisms. So to conquer this standard, we have to be aware of the properties of triangles, quadrilaterals, polygons, and things of that sort. So this could include things like knowing the interior angle sum formula is the same for convex and concave polygons. Also, geometry congruence number 9, prove theorems about lines and angles, and it gives some examples below that. In proving that the interior angle sums of the convex and concave polygons are the same, we have to use theorems about lines and angles to be able to do that. And the last content standard is geometry congruence number 10, prove theorems about triangles, and there's some more listed below that one too. So in proving that the formulas are the same, we have to know that the sum of the interior angles of a triangle are 180 to be able to do that. I also thought SMP 7 related to the question, which is look for and make use of structure. This SMP is all about recognizing patterns and being able to use those patterns. So to prove that the sum of the interior angles of any polygon is the same requires the students to see patterns and then use these patterns to make conjectures about them to create the formula. So for the math I need to know, the first thing I need to know is what a polygon is. So a polygon is a two-dimensional geometric figure with these characteristics. It is made of straight line segments. Each segment touches exactly two other segments, one at each of its endpoints, and it is closed. So it divides the plane into two distinct regions, one inside and the other outside the polygon. I also need to know the difference between a concave polygon and a convex polygon. So a concave polygon is any polygon with an angle measuring more than 180 degrees. Concave polygons look like they are collapsed or have one or more angles dented in. And a convex polygon, then, is any polygon where all of the angles are less than 180 degrees. Since we know that if the angle is 180, it just forms a line. So if every single angle in the polygon is less than 180, it's a convex polygon. And if it has even just one angle that's more than 180, it is a concave polygon. So I also need to know the formula for the interior angles of any convex polygon, and I need to know where the formula comes from. Okay, so I'm going to go through 3 methods for proving the interior angle sum theorem for concave polygons. So we'll start with this first method, method 1. So I just have to draw a polygon, and it can be any polygon. It doesn't have to be regular or anything, just any polygon. And this one has 7 sides. So what we're going to do for method 1 is we're going to pick any vertex. So we'll just choose this one here, and we're going to draw diagonals from this vertex to every non-adjacent vertice. So now we've created triangles within the polygon, and if you notice, there are n minus 2 triangles, where n is the number of sides. So if you count, we have 1, 2, 3, 4, 5 triangles. And notice that each vertex of each triangle shares at least one part of the vertice of the original polygon, and that each vertex of the original polygon is made up of at least one part of a triangle vertex. So then the sum of the angles of the triangles is going to be equal to the sum of the interior angles of the polygon. And since we know that the sum of the interior angles of a triangle is 180, we can multiply that by the number of triangles within the polygon. So here, where n is the number of sides, we have n minus 2 triangles. So multiply that by 180 degrees, and that is going to give us the sum of the interior angles of this polygon. Okay, so then we have method 2. So we're just going to draw another polygon. Doesn't have to be regular or anything again. And then we're going to draw a point O within the polygon. So it just has to be somewhere inside of it. It doesn't have to be necessarily in the center, but just somewhere inside. So we're going to label this point O, and then draw lines from point O to each vertice. And notice that this time that not all of the vertices of the triangles share some part of the vertice of the original polygon. So the sum of the interior angles of the polygon is going to be equal to the sum of the angles of the triangle minus the sum of the angles surrounding point O. So the sum of the angles of the triangles is going to be 180 multiplied by how many triangles there are. And in this polygon, we have 6 sides, and we also have 6 triangles. So the number of sides and triangles are equal. So if we take, we're just going to call it n, the number of triangles, and multiply that by 180. And then we want to subtract the sum of the angles surrounding point O, which is 360 surrounding point O. But 360, that's also equal to the sum of the angle measures of 2 triangles, so we can write it that way. So n times 180 minus, minus 180 times 2. So now if we factor out 180, we get this expression for the sum of the interior angles of this convex polygon. So now we have method 3. So we're going to draw another polygon. So this one has 8 sides. In this method, we just want to draw diagonals in the polygon with the goal of filling the polygon completely with adjacent triangles. So we want to fill all of the space in the polygon with triangles. So we're just going to start drawing diagonals. So now you can see we have 6 triangles. And again, all of the vertices of the triangles and the polygon are shared. So we can say that the sum of the angles in the triangles are going to be equal to the sum of the interior angles of the polygon. So again, with this method, it's very similar to method 1. We're going to arrive at n minus 2 times 180. So the next thing I need to know is how the methods for proving the formula for the sum of the interior angles of a convex polygon relate to proving the sum of the interior angles of a concave polygon. I need to know which methods can be used for both convex and concave and which cannot. And I also need to know, this next part I got from our book from the class, that even though the formula for the sum of the angles stays the same, the area does not. So I'll get to why that is important in a minute. So I'm going to start with this crazy looking concave polygon. It has 11 sides. So what we're going to try to do is we're going to use the methods that we just went over and see if we can get the same formula using one of those methods. So if we look at method 1, that was where we start at one vertex and draw diagonals to the other vertices. We can't really do that with this polygon because there isn't really one vertex we can see where we can draw a diagonal to every other vertex. So that method is not going to work, method 1. So we can think about method 2, where we draw point O somewhere inside, not sure where that happened, somewhere inside of the polygon, and then try to draw lines from the point to all the vertices. But there isn't really anywhere inside of this polygon where we can pick a point and do that. So method 2 is probably not going to work either. So we can think about method 3, which is just trying to fill the polygon with triangles. So let's try that and see what happens. I'm gonna pretend those are on the vertices. Okay, so this is filled with triangles. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles inside here. Oop. 9 triangles. So you can see we have where n is the number of sides, we have n minus 2 triangles in here, and all of the vertices of the triangles and the polygon are shared. So we can arrive at the formula of n minus 2 times 180 degrees. Okay, so now we have this new polygon. It has 4 sides. And you can see pretty much all the methods will work depending on how you use them. So we could draw a diagonal from B to D, and that can pretty much work for either method 1 or 3. We could also draw a point in the middle here and connect that point to all the vertices and end up with 4 triangles, the same as sides. So I'm just going to go with method 1, which is to draw this diagonal from one of the vertices to all the other non-adjacent vertices, which there only happens to be one diagonal. So we end up with 2 triangles. So again, we can arrive at this conclusion. And I'm sure you can probably see that method 3 is probably going to work almost every time. The other methods, if it's a if it's a concave polygon, it really just depends on what the polygon looks like, if you can use it or not. And so the reason I mentioned that even though the formula for the interior angle sum stays the same for convex versus concave polygons, the area does not, is that students may get confused about the formula, about formulas in general relating convex and concave polygons, because they may think that since there is a relation between these, that they're the same. Maybe that's how it works for other formulas too, but that's not the case. So for this one, like, we can't use length times width or length times height to try to figure out the area. We would have to kind of figure it out in other ways. So it's important to point out to your students that even though this formula is the same for convex and concave polygons, that's not always going to be the case. Okay, so for my response, I want to show how the interior angle sum of a convex polygon can be determined by counting how many triangles make up the shape, which for the context of the problem, this was probably covered, but I'm just going to go over it just in case. Then I want to draw a concave polygon with the same number of sides and show that there are still the same number of triangles within the shape, and use GeoGebra so that I can move an angle around and make a polygon convex and concave and back and forth, and they can see that it's going to be the same either way. So here we have a concave polygon, and you can see that if we draw lines here, make triangles within the shape, that we're going to have 4 triangles within this 6-sided polygon. So 4 times 180, we should have 720 degrees within this convex polygon. If you look up, I have the formula here. So all of these angles added together are going to be 720 degrees. So what about this concave polygon that also has 6 sides? So we can try again to make triangles on the inside here. See how many we get. All right, so we're still going to get 4 triangles within this 6-sided polygon. So the sum of the interior angles should again be 720, and you can see over here that it is. And at this point you can see that it doesn't matter if, oops, it's not what I wanted to do. You can see that if you move things around, the sum over here isn't going to change. And if I make this concave polygon and make it convex, the sum of the angles won't change. These will change, the individual angles, but the sum of the angles is never going to change. So for my follow-up question, I would draw a convex polygon, and I would ask that if I took 2 angles and I took them in to make the polygon concave, would the sum of the interior angles remain the same? Why or why not? And what would be the sum of the interior angles? And so hopefully after that explanation, it should be pretty easy to answer this, but this would help me gauge if they understood the explanation. They should be able to say that the sum would not change if they have the same amount of sides, whether it's convex or concave, and they should be able to tell me why that is, and tell me what the sum of the angles are. And so here are my resources that I used for this presentation. This is a journal article from the mathematics teacher, and it gave, it's a really good source for proofs and explanations on the interior angle sums of convex and concave polygons. Sometimes it's kind of hard, actually it's pretty hard to find information on concave polygons apparently, but this gave some really good proofs that I actually used in my presentation. And if you are a teacher and you want to know more about this subject, I recommend looking into this source. I also use this source just for some geometry definitions, so polygon, convex polygon, concave polygon. This source is our textbook. I use this for some information on similarities and differences of equations for convex and concave polygons. And I also found, here's a video online that can be used as a resource, again, for teachers if you do want to find out a little more about convex versus concave polygons. So that was my presentation. I hope you enjoyed.